The following figure is used for questions 15 and 16. A small block of mass m is moving on a horizontal table surface at initial speed VO. It then moves smoothly onto a sloped big block of mass m. The big block can also move on the table surface. Assume that everything moves without friction. A small block moving with initial speed VO moves smoothly onto a sloped big block of mass m. After the small block reaches the height h on the slope, it slides down. Find the height h. So to illustrate what's going on, so we have a small mass with a speed, constant speed, and then it's gonna hit the big block. Right before the collision, and then at one point it's gonna reach the height at which the block stops from moving, and we have to find the height. Alright, so because collision is involved, I'm gonna use the conservation of momentum to solve this problem. Conservation of momentum. So we have mvo plus big M, big initial velocity. So this velocity pertains to the big block's velocity, but you will notice that that's zero because this block is not moving until it collides, and equals m plus big M because they are now combined mass and they have the same kinetic velocity. So I can cancel out the one that's zero, and depending on what we need in our conservation of energy equation, we'll rearrange this for specific cause. So another equation you need is conservation of energy. Very often you will see that conservation of momentum and conservation of energy are very coupled to solve these types of problems. So conservation of energy is kind of big here because we have many things going on. You have kinetic energy of the small, and then you have kinetic energy of the big, potential energy of the small, and potential energy of big equal kinetic energy of both big and small, and I'll explain why. Oh, actually I already did. You see that both blocks are combined as one system, so I write both here, and then plus potential energy of small and the potential energy of, okay, don't forget it's final, and potential energy of the final for the big. So what you notice is that the big block is only moving horizontally, therefore we can simply cancel out the potential energy of big in the system, and also the big block was not moving initially, so you can cancel that out as well. And also the potential energy of the small block is zero if we call y equals 0 as our ground, so that also reduced down to 0. So that gives us only these three components to play with the numbers, well actually the equation. So I'm gonna have 1/2 mv squared for that kinetic energy, and then combined mass of the kinetic energy is 1/2 m plus big M v final squared, and then the small potential energy is now mgh. In other words, you start out with the kinetic energy of the small box here, small block, and then that's now converting it into the kinetic energy of both combined small m and big M, and also it's divided into the potential energy of our small block. And we're ultimately looking for that height here. So I'm gonna write that in red font so that you know what we're trying to achieve here. So we have to use our equation 1 and equation 2. Looking at our choices, I see that VF that you see here, the big VF, is not involved in the choices A through E. Therefore, we can now rearrange the equation 1 as VF. So VF is simply equals to, just divide both sides by the M plus big M. So you get MVO over M plus big M. Okay, you can replace that now. Replace this with here. Don't forget to square, however. So we have 1/2 MVO squared plus 1/2 M plus big M you get squared on both top and bottom plus MGH. Notice how M plus M, the big M, cancel out. But you can only cancel out the exponent now because you still retain M plus big M on the denominator, except it's not squared anymore. So we're still looking for the height. What else can we reduce? Now notice that we have big M, small m, and small m. So I'm going to distribute that, the m squared and v squared. I'm going to distribute that squared here so that I can cancel out better. So when I cancel out the small m, okay, it's gone on both the left side and the MGH part here, but I cannot completely eliminate m, except I can just reduce that exponent to 1. So also I can also multiply both sides of the equation by 2, so that gives me v initial squared equal 1/2 m plus big M, that's in the denominator, and on top I have MVO squared plus GH. But we want to find an H, so I'm going to subtract this, the middle term, or I'm going to switch this to the left side. And and another thing, I just multiply by 2, so this 2 also gotta be multiplied here and here, right? So I'm not gonna have 1/2 here. I'm not gonna have 1/2. So let me also write 2 is multiplied on the right side. So over here we have to have 2GH. Okay, so it looks good now. So V initial squared minus this middle term equals 2GH. Okay, now I can have a common denominator on both sides like this. So I have m plus big M and then also I can divide by 1 over 2g, and that is equal to our desired height of smaller block. Okay, you will notice that some terms cancel out on the numerator. So our final answer for our height is mv initial squared over 2gm plus big M, and we have the answer here, C.